Hey guys, I'm Jed. Welcome back to my LeetCode review one take vlog on 211th problem. Design, add, and search words data structure. We need to design a data structure that supports adding new words and finding if strings matches any previously added string. We need to implement the word dictionary class here. The word dictionary constructor initializes the object. The add word method adds word to the data structure. It can be matched later. And the search method returns true if there is any string in the data structure that matches word or false otherwise. Word may contain dots, where dots can be matched with any letter. And let's take example 1 here. We create an empty word dictionary class instance. Then we add 3 words, bad, dad, and mad. Then we try to search several words. We try to search pet, we got false. We search bad, we got true. And we try to search bad, we also got true. And we try to search dot, add, we got true because bad, dad, mad matches dot add. And then we try to search b double dots, we got true because it matches bad. Then let's get started with the intuition of this problem. After looking at this problem, we need to implement a data structure that supports 2 main operations, adding words and searching words, with a spatial pattern matches feature, which is the dot matches any letter. Our first thought is to use a try since we are dealing with strings and prefix operations. Try is also called prefix tree. A standard try would work well for adding words and exact searches, so we need to extend it to handle the wildcard character dot. And we can think of few approaches. The first approach is called brute force. We can store all the words in a list and perform pattern matching for each search. By the time complexity, it is big O of n times n for each search, where n is the number of words and m is the average word length. So we can also come up with the second approach called try with backtracking. We could use a try for efficient storage and implement a recursive search helper method that explores all possible paths when encountering a dot. This method would be more efficient for exact searches and reasonable for wildcard searches. So let's get started with try with backtracking method. Inside code, first we need to declare a private class called tryNode, which will be the building block of a try. Private class called tryNode, and we'll declare 2 variables. First is tryNode array called children. Each node has up to 26 children, and each one of 26 children is for each lowercase letter, which is A to Z. Then we declare a boolean variable called is end of word. Then we need to declare the constructor of the tryNode to initialize a new tryNode instance. Public tryNode constructor. Inside it, first we need to initialize the children array with 26 letters. Children gets new child node at size of 26. Then we initialize the is end of the word variable as false. Is end of word gets false. Then we also need to declare a root child node variable to help us solve the problem. Child node called root. Then we need to implement the word dictionary constructor. We just create a new root node where when the dictionary is created, root gets new child node. Alright, then we need to implement the add word method. First, we need to start at the root of the child node called current gets root. Then we create a enhanced for loop to iterate through each character in the word for character C in word to character array. For each character, we need to calculate the index for this character. For example, A is related to 0, B is related to 1, and so on. Integer index gets C minus character A. If the child node for this character doesn't exist, we need to create it. If current dot children of index equals now, then we'll create a new child node. Current dot children of index get new child node. Then we'll move to the child node for the next iteration. Current gets current dot children of index. After that, we will mark the last node as the end of a word. Current dot is end of word. Yes, true. Alright, that's all of the code for this method. Then we need to implement the search method to search for a word in the dictionary. But as we mentioned before, we need to create a search helper method to help us recursively search with the wildcard support. So let's say we'll create a method called search helper. And this method needs 3 variables. First variable is the word, and the second variable is the index, and we'll pass 0 here. And the third parameter is the node, and in this case we'll pass the root node. And then we need to declare and implement the search helper method with 3 parameters. First parameter is a string word. Second parameter is integer index. And the last parameter is child node, called node. Alright. Inside this method, at the very beginning, we need to handle a bad case. If we've processed all characters in the word, then we just return node.isEndOfTheWord. if index equals word.length. Then we return node.isEnd of word. Next, we need to get the current character we are processing. Character C gets word.character at index. Then we'll check if the current character is a dot or not. If character C equals character dot, then we'll check all possible children, which is all 26 letters for integer I started at 0. When I is less than 26, we'll increment I after each iteration. Inside for loop, first we'll check if the child exists or not. If no.children of I is not equal, it's not equal to now. Then we'll recursively search with this letter and the next character, this child and next character. If search helper of words index +1 node.children of I. If so, we'll return true, because if any path leads to a match, so we need to return true. On the other hand, if no path leads to a match, we'll just return false. On the other hand, if the current character is not a dot, which means the current character is a regular letter from A to Z, so in this situation, we need to calculate the index for the character. Character index gets C minus character A. Then we'll check if the child for this character exists or not. Node.children of character index equals now. Then we'll return false. Otherwise, we'll recursively search with the next character. Return search helper with word index +1 and node.children of character index. Alright, that's all of the code. Oops, I forgot a semicolon here. Let's resubmit the code and check if a solution passes all test cases. Yes, our code got accepted. Now, let's analyze the time and space complexity. So, for the time complexity, we need to analyze two situations. First is add word. The time complexity, it is big O of M. M is the length of the word, because we need to traverse each character one time. And for the search method, it is, and there are two cases. First is the based case, which means there's no dots. No dot. The time complexity, it is big O of M. M is the length of the word. But in the worst case, all the characters are dots. So we might need to explore all possible paths in the try. However, we are given the constraint that there will be at most two dots in the search queries. So the practically complexity is much more reasonable. And the space complexity it is big O of m times n. N is the number of words and m is the average word length. In worst case, if all words have unique prefixes, then we'll have a node for each character of each word. And the second factor is the recursive call stack for search can go up to big O of m depth. And this is the end of my LeetCode review blog on 211th problem. And I highly recommend you guys to visit my online GitHub page here, which contains all the problem description, enunciation, and the solutions with very detailed codes and explanations and the final time and space complexity analysis. You can also visit my GitHub repository here, which contains all the codes and notes to build this online GitHub page. And I'll put those two links on my YouTube description below. And thank you guys for watching. I'll see you next time. Bye bye.